Hello class, in this lesson we're going to learn about properties of volume. So many of the properties of volume are analogous to the properties of area that we already learned. So let's look at them side by side. So volume is a positive number that tells you how much space a solid takes up, but not necessarily what the shape is. And in order to calculate the volume of a rectangular or triangular prism, we just multiply the area of the base times the height. If we have congruent solids and they have the same volume, and if we have overlapping solids, to figure out the volume of the union, so if you put them together, you calculate the volume of each piece, and you subtract the intersection where they overlap. So volume of A plus the volume of B minus the volume of this rectangular prism in the middle. If we have a solid with another solid cut out of it, in order to calculate the volume, you subtract. Calculate the volume of the larger one here, B, and subtract the volume of the smaller one, A. And just like we were able to form estimates for area by using squares and triangles, we can do the same with solids and volume by using rectangular prisms and triangular prisms. So as a little warm-up, I'd like you to use what you know about the area of rectangles to deduce why the area of a right triangle is 1/2 the base times the height. So try that and I'll show you my solution. Well, you know that if you did a rotation, you'd have two right triangles that would form a rectangle. And so it would be half of the area. You know the area is base times height for a rectangle, so take half of that, 1/2 base times height. Now using the same train of thought, we can use what we know about rectangular prisms and their volume. So what you know about this rectangle on top, now you can figure out the area of one of these right triangular prisms. Well, we know since it's a rectangle, that these two areas are the same, so the volume of the rectangular prism will be 2 times AH. And so if you take half of that, you would just get AH, the area of the base times the height for the triangle. So we want to use these prisms in order to figure out the volume of any general right cylinder. Now, we only know how to figure out right now the volume of a right rectangular and right triangular prism. How could we extend this so that we could figure out the volume of any type of triangular prism? Maybe it has an obtuse base or an acute base. How could we do that? Well, let's look at the bases. How could we tweak the bases so that they both have right triangles in them? What could we do to them? Well, you can always drop an altitude to the longest side, and that can be done with any triangle. You can always form 2 right triangles with it. And we know how to calculate the area of each half of that. So to figure out the area of the triangle, just add up the area of the 2 right triangles. And we can extend this to the prisms. We can split up the prisms into 2 different prisms that each have right triangular bases. And so how's that going to help us calculate the volume of any right prism with a triangular base? Well, you're going to break it up into smaller right triangles and calculate all their volumes and add them together. That's going to get you the volume of the entire prism. So to practice, I'd like you to try to divide this region into triangles and give each of your bases and heights a value and figure out its area. So you're going to probably pick different numbers than I pick, but you should split it up in a similar way. And using your measurements, figure out the area of your polygon. So try that and I'll show you my solution. Here's how I split it up. And we have 3 right triangles here. And if we figure out the area of each one and add them together, we get 241 square units. Now, if we extend that to what we just did to volume, and we know that the height of the prism is 10, how can we figure out the volume of this prism using our previous answer? Just multiply the area of the base times the height. So 2,410 cubic units. Now, what if the base isn't necessarily something that's a nice polygon? What if it's circular or some other type of region? How can we figure out its volume? Well, remember what we did with the area. We found a lower approximation and an upper approximation. Then kept making them nicer and nicer until it got really close to our answer. So think about what we do in 3 dimensions in a similar case. Well, we'd still do the same type of approximations for the base. So we're just looking at this base down here B, and still approximate it the same way. But instead of just looking at area, we're going to project these into 3 dimensions. So we're going to end up looking at prisms here. So we multiply each area of each base here by the height in order to figure out the volume of each prism here. So this is partially done so you can see what's going on. So you would do this for every single polygon we have in our approximation, and you would get an approximation for the volume. So the true volume is going to be wedged in between the volume of our two approximations, just like it was for area. And this inequality shows that. Here we have the area of the smaller one, lower approximation times the height, which is volume, and the area of the upper approximation times the height, which is the upper volume approximation. So the true one is in between those two. So here are a few very common volume formulas, and you're given these on the reference sheet on the Regents exam, which is nice. I suggest you still have them memorized so that it's a lot easier to go about solving these problems. Now note that for the general prism and the cylinder, these are really the same formula. You're just rewriting the base as the formula for the area of a circle. And same down here. Instead of B for base, you have the formula for the area of a circle. A very common application of volume in math and science is when we're dealing with density. So we're going to do a few practice problems on density. Here we're given the density of a square metal plate, 10.2 grams per cubic centimeter, and we know its weight in kilograms. We want to calculate its volume. So we're going to use this formula, density is mass divided by volume. So we got to make sure that we have proper units. Here we have kilograms, but this is in grams per cubic centimeter. So we really should convert kilograms to grams first. So how do we do that? Multiply by 1,000, right? 1,000 grams in a kilogram. And we get 2,193 grams. So try to solve the problem, try to figure out what the volume of the plate is, and then I'll show you my solution. So hopefully you wrote an equation similar to this. The density is the volume, is the mass divided by volume. And we can use the cross product there. Get 10.2 V is 2,193 divided by 10.2, and you get 215. So now that we know the volume, how can we figure out the thickness of this plate? So remember, it's a square metal plate. We know its volume and the area of the base. How do we find the thickness or the height? Well, we know that volume is the area of the base times the height. We're using the letter A for the area of the base. Sometimes use capital B. It really doesn't matter. Divide by 25, and we get 8.6 centimeters. Similar example, I'd like you to try to approximate the density of water by using the information that's given in the problem. So try this, and I'll show you my solution. So remember, density is mass divided by volume. So we got to figure out the mass of the water and divide it by the volume. So to figure out the mass, we have the cup with water, and that's 1,000 grams, and the cup is this amount of grams. So we subtract them and figure out the mass of the water. Now we got to figure out what's the volume. Well, it tells us it has a diameter and height of 10 centimeters, so it's a cylinder, a circular cylinder. So it's going to be pi radius squared times the height. So if the diameter is 10, the radius is 5, and the height's 10, they give us that. And so we get 250 pi. We're not going to round to the very end if we need to. So for the density formula, we divide the mass and the volume. So we get these numbers, and if we divide the rational numbers, if we leave pi in the denominator for now, we end up with 3.1416 over pi, which when you round it is about 1. So according to this experiment, the density of water is about 1 gram per cubic centimeter. In a previous lesson, we learned the scaling principle for area. And that says that if we know the scale factor between two figures is r, then the ratio of the respective areas is r squared. How do you think that works for the ratio of volumes for similar solids? How do you think the volumes are related? Well, hopefully you said by a factor of r cubed, or r to the third power. So let's try that experimentally. Let's see if that's true. So we're going to go through 3 pairs of solids. I'd like you to calculate the ratio of the side lengths from A to B. So A is the one on the left, B is the one on the right. And figure out the ratio of the volumes. We're going to see what's going on with those numbers. So try this for the cones, and then I'll show you my solutions. So the ratio of the sides in simplest form is 5:4. And we calculate the volumes. That's 1/3 pi r squared times the height. That's how we get these numbers. And when you simplify, you get 125 to 64, which is the same as 5 cubed to 4 cubed. Let's look at these rectangular prisms. Try the same thing, and then I'll show you my solutions. So you look at the sides, and they have a ratio of 1 to 5. And if we look at the volumes, it's a ratio of 1 cubed to 5 cubed. They're just showing here how you can simplify step by step by using different factors. So first they divide by 2, and then by 3, and we get our cubes here. And finally, these triangular prisms. Figure out the two ratios. So the ratio of the lengths is 1 to 3, and the ratio of the volumes is 1 to the third to 3 to the third. And so that gives us our scaling principle for volume. What do you notice about these relationships? Just like we thought would happen. The ratio of the volumes are the cubes of the scale factors that relate to two similar figures. So here's the same scaling principle to put into terms of volume and R as the scale factor. So this is a very important property to know. So we're going to see here what happens if we scale differently in perpendicular directions. So first, what's the volume of this triangular prism? Try part A, and I'll show you my solution. It's going to be the area of the base times the height. The base is a triangle, so 1/2 3 times 3 times your height gives us 45/2, which in decimal form is 22.5. And let's say units cubed because they don't give us any units. Now, what if we scale the base in one direction by a factor of 2, in the other direction on the base by a factor of 4, and the height by a factor of 3? What are the new dimensions? So I'll go back up so you can see them. So factor of 2, factor of 4, and factor of 3. Well, we multiply. So 3 times 2 is 6, 3 times 4 is 12, and 5 times 3 is 15. Now, using those dimensions, what would the volume of our scaled triangular prism be? Well, we use the same idea, but now we have our new dimensions. You get 540 cubic units. And so what do you think is going on between this volume and the original volume? Well, the original volume was 22.5. And this one is 540. How are those related with what we did? Well, it's what we get if we divide them, we get the product of the scaled factors that we used. So if we had instead just multiplied the original volume by 2 times 3 times 4, we would get 540. That's exactly what this says. This is a generalized version of the scaling principle for volume. So if we're scaling in 3 perpendicular directions with 3 different scale factors, you just multiply them all together. And in the case when you have similar solids, these would all just be R, so it would be R cubed. So this is really the same formula, just generalized. And finally, we have one more application of volume and density. So try to solve this problem. I'll figure out which of the boxes is more cost effective, and then I'll show you my solution. So for the first one, for the 5-inch cube, we have to figure out the volume of the cube and subtract the volume of the widget. And so we do that, and we get 85 cubic inches of foam packaging is what we need to buy. And for the standard box, it has a cost of 80 cents each. And we also have to add in the cost of the foam. So 80 cents plus 3 cents times the 85 cubic inches gives us a total cost of $3.35. Compared to the specially designed box, which is $3 each, the specially designed package is more cost effective. In this lesson, we learned about different properties of volume. Thank you for watching this video.